my goal is to bring everybody kind of together to a certain level in terms of the optics background. So I like to start first with some undergraduate slides that I use for my course called Optical Imaging in the fall, and basically dealing or reviewing linear systems and Fourier transforms very quickly. How many of you know what the Fourier transform is? Great. And I assume you also know what a linear system is. You don't need to raise your hand. But to make sure, we'll review this very quickly. And then, why is this important? Because we're going to be using the Fourier transform and its properties repeatedly. And then we're going to go back to Maxwell's equations and start from there. So how many of you know Maxwell's equations? Okay, I notice fewer hands. So I don't feel that the lectures are useless then. There's a lot of material that I plan to cover today, this morning and in the afternoon. The thinking is that some people will be more familiar than others, and those who are not, hopefully should take the time to also read at home a little bit, maybe. And so I regard this as a review, so I'm trying to go basically quickly. Okay? So we'll take a break every something like an hour, 50 minutes, and then come back and so on. We'll do that a few times today. We'll see how it goes, okay? Okay, so we want to develop a set of tools, but since this is not a math course and I'm not a mathematician, I want to try to start with the real problem. And the problem I'd like to discuss with you is the one that you've seen probably since you were a kid in high school, and that is the mass on a spring. So you have a certain mass that is hanging off a spring. The spring has a certain elastic constant. And what we want to find out is the displacement of the mass as a function of time. That will be the solution of this linear differential equation, where I have an acceleration term, I have a damping term, and I have a resonant term or a restoring force, and this possibly an external force. Okay, so I can pull on the mass with a certain function that could be very general as a function of time. My goal is to find out what x is. Okay? If I define the operator L like this, that includes all the differential operators in it, I can write my equation simply like L of x equals f of t, where f is this f. Disregard the mismatching font. Okay, so basically I can write in a very compact way my differential equation like this. This this linear operator has very interesting properties. One is that if I apply it to a constant times x, okay, so this is just a scalar, a constant. You can think of it as a number. L of ax is actually a times L of x. Okay? So I'll tell you in a minute what that means, and I'm sure you've seen this in many linear operators before. And another thing is that if I apply it to two different functions, x and y, L of x plus y is going to give me L of x plus L of y. So now you may wonder, what is this to do with our optics, with anything, with a mass on a spring? I know most of you know this, but basically it allows us to solve a complicated problem, to break it down into smaller pieces. So, for instance, I can have a certain force applied to the mass on a spring, and then I have another force, F2. The fact that this is a linear operator, it tells me that I can solve each problem separately. Okay, L of x equals F1, and then L of x equals F2. And in the end, I add the results, x1 plus x2. And this is very, very important because I can break down the problem that is very general and could be complicated into smaller pieces that are easily tractable. Okay? So again, the operator that verifies those two properties is called a linear operator, and it just happens that the linear combination of differential operators is a linear operator. So here's one kind of corollary or one consequence of this. If x1 and x2 are solutions to the problem, to the mass on a spring. So I have a certain force that acts on a spring. The spring has a certain constant. I have certain friction and so on. And I have two solutions, x1 and x2. It turns out that a linear combination of x1 and x2, that means ax1 plus bx2, that is also a solution. Okay? And again, what that means from practical purposes is that I can take a complicated problem and break it into pieces that are simple. Okay, this can be generalized for n degrees of freedom and so on. Let's go back to our optics. Why is the mass on a spring so important? Is that more than 100 years ago, Lorentz came up with a model that explained optical properties of materials to very, very good accuracy, just based on a charge, an electron that's connecting to the nucleus, similar to, in the same way as a mass is connected to a spring. There is a restoring force, there is an attraction force between the electron and the nucleus. There's possibly some loss in the system. That Lorentz actually had problems kind of explaining where the loss was coming from. Now we understand that the loss in a material comes from the electrons bouncing in a lattice with various atoms, therefore losing energy. So that acts as a damping term. That acts as a viscous, as if you're putting the mass in a viscous medium and you damp energy. Basically, it transforms into heat. So this model of mass on a spring is, Lorentz used this to explain properties of the optical material, and we're going to talk in detail about that. And basically, he came up with the concept of a resonance of an optical material that is very similar to the resonance of a spring, that relates to the mass that we attach to the spring and the elastic constant K. Okay? This, in the atomic model, this corresponds to a certain resonance of the atomic system that we know is very important in terms of giving the optical response of that material. Okay? So this is the connection between, in case you're wondering why do we talk about mass on a spring, optics is coming right up, okay? So basically, I can talk about the electron having a certain displacement x. The differential equation that describes the motion of that electron is exactly the same, except that this force now is due to the applied electric field. So I have, let's say, a laser beam that comes incident on a piece of glass or anything else. And the electric field coming from my optical beam acts as an external force to the charge in the material. So again, our problem is to solve this equation. What is x as a function of t, given all these properties of the material, right? So there is a property of the material in this gamma. So in optics, keep in mind that means how the electrons are bouncing with the neighbors, giving up energy. Can you tell me which material would have a larger gamma, a piece of metal or a piece of glass, without knowing anything? What do you think? Anybody? In metal, why? That is correct. Exactly. So in a metal, we have the charge is, so to speak, more free to move around, right? That means conductivity is much higher than in a piece of glass. Thank you. So that's the reason, just without knowing anything, that's how I think Lorentz was thinking about the problem. So this gamma is something to do with the conductivity, right? Is how free the charge is to move around and therefore lose energy. And this is something to do with the resonance in the system. So how do we solve this problem? Again, linearity is something that is very important. So applying the concept of linearity that we mentioned in the beginning now to light-matter interaction. So you can think of it this way. You have two electric fields applied to a piece of material. Okay, so imagine this is our glass. And the linearity allows us to solve each problem separately and add up the results. Okay, so it may sound very kind of trivial and kind of a simple concept, but it's very, very powerful. Okay? Again and again, the reason is that I can take a very complicated system, imagine, or input, I should say. Imagine I have a pulse that looks like this, completely, how should I say, very general. The fact that my system is linear allows me to take pieces of this strange looking pulse and making into some shapes that I like. In particular, I'm going to show you in a second, we like very much sinusoids. Okay? So, I take my general input, I break it into pieces that I understand, I know how to calculate fast, in the end I add the results. Okay? That's what I want you to remember from linear systems, at least in the concept of optics. So, each of the electric fields generates, so electric field E1 generates a certain displacement x1. Okay? If I know how to calculate that, that means I solve the solution for input E1. I solve it for input E2, I get displacement x2. Linearity allows me to just say that the response to E1 plus E2 is actually the sum of the two displacements. Very useful. This is called the superposition principle, which is applied pretty much in all branches of physics. Okay? So let's take it a step further. If my input field looks like this, so think of this as a pulse. Okay, I have a laser that emits this pulse, and my general problem in the lab is I would like to know what comes out on the other end. I have a piece of material, piece of crystal. I send this in. What is it that I get on the other hand, or at the other end of the material? Okay, something like this. I can get something strange like that. So basically, we call this input. The crystal or the material, we call that the system, and we call this what? Output. Now, there is a very important mathematical result that tells me that I can express any function basically as a summation of delta functions. Which basically says, kind of intuitively, that I can break this continuous function into these discrete bits. Right? It's like digitizing a signal. And if I properly shift these delta functions and I give them the correct amplitude, I should be able to recover the actual input. Mathematically, you can write this like this. This integral that is a basic, usually is presented as the basic property of the delta function, Dirac delta function. Which basically, what is this operation here? This one, this integral, what is that called? So I have a function of t prime, another function of t minus t prime, and I integrate over t prime. That has a name. Good, okay. It means that if I convolve any function with a delta function, I get the original function back. What is that to do with anything? Well, think about this delta function decomposition as my way of breaking the general input into small bits that I understand very well, that I can calculate very quickly. Okay? So remember, the idea is that with linearity, I can break the input into small bits, solve it for each bit, and add the results in the end. Right? So, what that means is that all I need to do to find the final solution, x of t, this is the response, this is the output of this input, is to add the responses to each of the delta functions. And remember, the delta function was, they were shifted at different positions. We call the response to delta, if I send the infinitely short pulse through the system, I get out h. I just call it h. What I get in the end is summing out all those h's with the proper amplitude given by the input, okay, and with the proper shifting. Probably I should point to t prime. Okay, so this integral is again adding the responses to all the delta functions, shifted at the proper position and with the proper amplitude, which I just showed you comes from here, right? So there is an amplitude at this point, another one here, and so on. So what does this mean? It means that the response to a general input E of t is the convolution between that input and the response to a delta function. Okay? So this is all due to linearity. You didn't have to know anything, just the fact that if in a linear system, if I had two inputs, the output of this combination is the sum of the two outputs. Okay? All we did was to generalize this for this delta function deconvolution, and that's the result. What do you think about this? I think this is very important. I can do it in reverse. What do you mean? If you wanted to know how the functions derived, let me rephrase what you're saying. All we need to know about my system is h. Right? How do I measure h? Experimentally. What would that mean if the problem was short pulses on a crystal? What would h mean in that case for that problem? Delta function. That means I have a pulse that is very, very short. I cannot make it delta function, unfortunately, but I can come, let's say, close. So to characterize fully the linear response of my crystal, I make the pulse as tight as I can, fire it to the crystal, measure it on the other end, and I will get something out. That will probably, most likely, will be broadened, right? For one thing, there will be some phases in there too. So that's how I measure h. Once I'm done with that, that means I can solve any problem that will ever, the solution to any problem, to any input that will ever hit that crystal. As long as the problem stays linear. That's important. Okay? So this is called the Green's method, or h is called the Green's function. I found that actually physicists call it the Green's function. Give me a minute. Engineers call it the impulse response for obvious reasons. It's the response to an impulse. They all mean the same thing. Bottom line is, this is very, very useful result. All I need to know is the response to delta function, and then I can predict the response to any general input. Any pulse that I can ever construct, I should be able to resolve it this way. Yep. Yep.
The further away you diverge from that, how imprecise does your answer become? How quickly does that diverge?
So this is a practical question. What happens from a measurement point of view if I cannot generate a delta function, right?
So how bad can your delta function be still useful?
Okay, let me give you a vague response, because that will depend on the situation. It has to be shorter than the scales of interest in your experiment. Okay? So if this is your input E of t and it looks like this, then you need to characterize h with probably an impulse that is much shorter than that. You don't want h and E to be or your input should not be comparable to the width of what you're trying to measure. Should be much shorter than that. Now, okay, yep.
How do you know the system is linear or not?
That's a good question. Well, I guess you try it. You try it. So let's talk about that. First of all, let me ask you this. We keep talking about time because it's kind of a direct, we have a good feeling about that. But can you give me the equivalent of spatial domain for this kind of result? What would be the equivalent of an impulse response or a Green's function in a spatial domain? The point spread function. You're getting very technical, but what does that mean? It means any imaging system, if I have as a sample a very tiny point, an infinitely small point as a sample, unfortunately that imaging system will not give us an infinitely small point on the other end. At the output is going to give us something of finite width, which we call point spread function in imaging. So basically I can write this in the spatial domain just exactly like this. In 1D, I can do it in 2D, I can do it in 3D, right? So this integral becomes, I need to input here R, which will be a vector, which will be an x, y, z. But the idea is the same. I put a delta function here, I get the camera, I image it, I actually get something that's broader. If the system is linear, all I need to know is the response to this very small point, and then I'm able to predict the response to any sample that I put in front of the imaging system. Now, how do you know the problem is linear? I would say just try it. One thing is, you don't want your, another way of saying the system is linear, you don't want your frequencies to mix in the system. So if you send short pulses to a crystal, and at some point your power is high enough that you get out some other frequencies, that's a sign that your system is no longer linear. Okay? You're going to learn a little bit about nonlinear optics today. Usually, you have a knob, so as long as you turn the power down, the power becomes more and more linear. To me, it's a little trickier in the spatial domain, where nonlinearities come from the fact that your samples are highly scattering. In other words, most cells, imaging most cells in under a microscope, they're transparent enough such that the differential equation that governs the light interaction with that sample, with the live cell, is linear. So the problem linearizes, you are able to express your result nicely, something like this convolution. And what we call that approximation or that assumption, we call it the Born approximation. Okay? That's an approximation where you say that the scattering from the sample is actually very weak. However, it starts to get complicated. If you look at some cells that are bigger, or if you look at the same cell, but now it divides and becomes spherical like this, and then the size of the cell with respect to the depth of field of your imaging system becomes important. It gets a little more complicated because of the 3 dimensions. To me, it gets more complicated than in the time domain. But I don't have a clear answer of how you decide it's linear or nonlinear other than trying it out. So any deviations from this kind of a convolution result will tell you that there is some nonlinearity in your system. Any questions about this? Do you have a good feeling about this? So I assume you don't know anything about linearity. This is a crucial result that will allow us to solve problems very easily in many branches of optics. So, yeah.
Known output, and you also do like linear estimation computationally, like mean square filtering.
Yes. Now you get into an area that's a little bit out of my field, but yes, people make a living out of this. So to to linearize nonlinear problems, basically. That's probably what you're talking about. If I can give you an example of just an intuitive example of how you do that. Imagine nonlinear effects in the mass on a spring problem is when you stretch the spring so much that actually the restoring force is not proportional to the displacement anymore. It's of a weird power, right? That means you stretch it too much, K starts, the elastic constant starts to change with the displacement. That's exactly what happens when you turn up the power of your pulse on the crystal. You start to shake the electron so much that the restoring force is no longer linearly proportional to the displacement away from the nucleus. Okay, that's what happens with the nonlinear response. But physically, you can do this. You can stretch it to a certain K. Okay, the problem is nonlinear, but now if you shake it around that little position. So we were talking about this. This is a nice linear problem, and now we stretch this guy and becomes nonlinear. So this is K1 and this becomes K2. Okay, that's clearly nonlinear because K depends on the displacement. But now what I'm saying is, if you manage to displace this just a little bit around this position, you can approximate the problem as linear again within that little approximation. Okay? So that's kind of a perturbation theory. But physically, this is what you mean. That what it means is that you find a new equilibrium position around which the problem becomes linear. Computationally, again, this is not my expertise. People use kind of iterative solutions to complicated problems. So you generate a solution, then you feed it back into your system, see kind of how good it is. Estimate, somehow define the goodness first of all, which is not an easy problem. And then generate another solution and another solution and so on. So nonlinear problems are tough. But we can do a lot with kind of approximating many problems with linear. I would say all problems are nonlinear, I think, absolutely speaking. But sometimes the linear approximation is good enough. Okay. Probably the the most useful tool in dealing with linear systems and some nonlinear systems is the Fourier transform. And all of you have heard of the Fourier transform, I think. You just told me that. The problem is like this. I think the way Fourier introduced his decomposition to the French Academy of Science was that he said something like this. If you give me a function that I can plot it on a graph, I can prove to you that I can write that function as an infinite series of sines and cosines. And all the academicians said, oh, that's nonsense. How can you do that? And it turns out he's right. And the way it connects to what we just discussed before, if you're able to do that, to have a graph, a function on a graph that looks very, how should I say, unordered, okay? Could be very general looking. The fact that I can decompose it in sines and cosines means that I can solve the problem for each of the sine and the cosine separately, which, intuitively speaking, should be easier, right? And then add the results in the end. That's why the Fourier transform is so powerful for linear problems. Because it gives me a decomposition for which I know usually the problem to each component, each frequency component is easy. And then all I need to do in the end is to add the results. So we need to be careful with the conditions for existence. But absolutely speaking, any field in any optical field should not have a Fourier transform. We can have a long discussion about it. But the fact that your measurement is finite in time, it comes down to that. The fact that your signal that you're measuring is finite in time allows us to use the Fourier transform and get actually the correct results. Okay? There are situations where that is not good enough to have a finite time, and that has to do with discontinuities. But we ignore all that. So for what you generally get in the lab on average, that condition is kind of taken care of. So if your signal allows for a Fourier transform, then basically the first result that you notice is that if you do the Fourier transform back of a certain function, you recover the function. What happens if you take the Fourier transform of a Fourier transform? By the way, I didn't define this because I assume you knew what it was. So the Fourier transform of a function of x is this integral right here, right? Again, it means you get more physical meaning if you write it the other way around. The function of x, I can write it as an integral f of, let's say, psi, e to the I, psi x, d psi. Okay? So it means this is cosine of psi x plus I sine of psi x. So it means that I can write my function f of x as the summation, that's what this integral does here, of sinusoids of frequency psi with the proper amplitude f of psi. So that tells me how much of each sinusoid I need to add. And f of psi is actually a complex function in general. Could be real, but it's a complex, which means that the phases are also important. In other words, I have this function that looks like this. The Fourier transform tells me that I can write it like a flat line plus a little bit of this frequency, and then higher frequency, and then higher frequency, and even higher frequency with various amplitudes. And if this is complex, that means it has a certain phase, and it tells me how I need to arrange these sinusoids, how they are shifted with respect to one another. This is the meaning of a Fourier transformation. I take a general function f of x, and I write it as a sum, infinite sum, an integral of various sinusoids of different frequencies with the proper amplitude and proper phase. Okay? Once I do that, all I need to do is to solve the problem for each frequency psi, and I add up the results. Okay? So what I was asking you was, what happens if I take the Fourier transform twice? So Fourier transform inverse changes the sign here, right? So if I take the Fourier transform, I change the sign here to a plus. By the way, the plus and minus is a convention thing. I noticed, again, physicists use a different convention from engineers. And on top of that, physicists use I, and engineers use J, or minus J. But anyway, forget all that. It's a convention. I'll explain to you what's my convention, but for now it doesn't matter. So what happens if I take a Fourier transform of a Fourier transform? Not Fourier transform inverse. Okay, so let me translate that. F Fourier transform of f of x gives me f of minus x. Thank you. Believe it or not, this is what a microscope does, or in any imaging system. Gives you that's what your eye does, by the way. So it takes the brain power then to switch the image upside down. So you take a Fourier transform and then another Fourier transform, you get the reverse image of the object, and then the brain does this. So we'll see how that works in a microscope in the spatial domain. Let's go back to our business. Quickly, you can see immediately that actually the Fourier transform operator is linear. There is no mystery here. You can just plug f of a times f plus b times g, you get this. So that means Fourier transform operator is linear. That means I can apply everything that we used before. Before we solve the Green's, before we put Green's equation, the one with the convolution between the input and the impulse response, we put it in terms of a Fourier transform. Let's go through a couple of, or I think 4 or 5 properties of the Fourier transform that will be more most commonly used in these lectures, at least in mine. Here's something very important. The Fourier transform of a function that is shifted. I'm not sure if I have a figure. So let's say this is x and this is f of x. Okay? The question is, what happens if I shift f of x by a? What's the Fourier transform of that? And again, I don't want you to think we're doing math here or undergraduate math. Think of those delta functions that reconstruct your general signal. There is a shift in there, right? So it's important to kind of find out the Fourier transform of a shifted function. So what is that? Well, it's right here. It's the Fourier transform of the unshifted function, this, times a complex exponential. In other words, Fourier transform of the shifted function times some modulation, right? Sinusoidal modulation. Can you think of a problem, optical problem, where this is important? Besides the one that I just told you with the delta function. Like a real problem, like a pulse or a diffraction, maybe. Anybody? Okay, let me help you. Let me go ahead of myself a little bit. I'll tell you this. If I have a field distribution E of x here, if you let this field propagate long enough, very, very large distance, I tell you without the proof that at the distance z that's very large, you get the Fourier transform of v, or something proportional to it, E of xi. Now, can you give me an example of a problem where the shift theorem is important? So propagation in far field over a large distance, that's the Fourier transform for you. We're going to prove that in the next lecture, but just take this for now, believe me. Eyeglasses? With lenses, you can take a Fourier transform too. We're going to prove that result too. With the lens, okay, if you ask about it, with the lens, actually, you can do the same thing, but much faster. You don't need to wait for a large distance. You do it right here in the back focal plane. That's what you meant? Okay. So if I put an input field, the same field here, I get the Fourier transform in the back focal plane of the lens. If this is exactly one focal plane before the lens. But still, my question is, how do we apply the shift theorem? There we go. So, that means what happens if I have two apertures, like this. And I have a plane wave, let's say, this uniform wavefront coming in. And I'm interested to know how the light from these two holes will look far away from that plane. Okay? Do you know what this experiment is called? Double slit. Hey, who did it? There we go. Young interferometer. Thank you. Why was this a historical experiment? Why was it so important? When was it done? Huh? Yes. Established the wave nature of light. So remember, Newton didn't like the wave nature of light. Okay, so whenever you get something wrong, don't worry about it. There are bigger people who got it wrong too. So Young did this experiment sometime in the 17th century. I don't know for sure. But the problem is very simple. You have two holes separated by a certain distance. And he showed that actually the light from here and from here talks to one another. Okay? And what you get in far field is something that is modulated by something like a cosine as you go up and down. So what I was trying to tell you was that the fastest way to solve this problem, the problem being I have an input, these two holes, the field in these two holes. This is the output that I want to find out. The fastest way to solve this problem is to use the shift theorem. How do you do that? Well, I know that each hole gives me the Fourier transform, so I would call this U1 tilde of psi. That is the diffraction from one hole. Okay? And the second hole will be what? E2, the Fourier transform of the second hole, of the field from the second pinhole, right? But now, I know that the field in the space U1 of x, if the pinholes are identical, which they are, is E2 of x minus a, where a is the distance between the two. So that means, based on the shift theorem, the fact that these are the two fields are just shifted by a constant a, that should allow me to use this property right here, right? So can you tell me what that means? So the Fourier transform of the second one will be what? Will be U1, the Fourier transform of the first one, times, there we go, E2 2 pi psi a. So how is the cosine coming out of this? Well, in far field we only measure intensities, right? And what is the intensity? Well, the intensity as a function of psi is the modulus square of U1 tilde plus E2 tilde modulus square. You see it? So it will be modulus square of this plus modulus square of this plus 2 times this cosine of this. So it will be something like, I don't know, some DC term that we don't care about, plus 2 times something something times cosine psi a. Of course, I didn't tell you what psi is. I will do that later. Psi is something to do, is proportional to the position across this plane. So clearly, without knowing anything, just this simple property of the Fourier transform, you are now able to solve pretty much, in my opinion, any diffraction problem. Okay, what happens if I add the third hole here? That's no problem. That means I have E3 of psi equals what? E1 of psi times e to the I, let's say if it's the same distance a, that will be e to the I 2 pi psi times 2a. Okay, so if I add another one, what happens? And so on and so on. So to get the full solution, we need to know the Fourier transform, in other words, the diffraction from one pinhole. And that I didn't teach you yet. Some of you may know, but we'll do that later. But once you know how each pinhole diffracts the light, adding many pinholes, it's a matter of adding these phase terms. And can you think of an experiment based on this that were other than the Young, using X-rays? It turns out this kind of general idea, and I put it in very simple terms, is what's at the bottom of crystallography, right? Where you're trying to understand how the atoms in a lattice are distributed with respect to one another. And because the distances are so tiny, we need to use something like a short wavelength. In particular, X-rays are pretty good with that. But the idea is the same. You see, these are your atoms. They pretty much scatter isotropically, each atom. So we don't care much about how each of them scatters. But what's important is these phase terms. And believe it or not, that was subject to several Nobel Prize activities. Okay, so all the respective positions of atoms in the crystals, believe it or not, are in that phase term. Okay, it all comes from this very simple property. Okay, let's move on. Any questions about this? As you can see, we have a bunch of slides for today, but I don't really have to finish them, so it's more important that we kind of agree. Okay? So don't be afraid to ask questions. I'm okay to leave the rest of the slides to you tonight for your private enjoyment. Are we okay with this? So what did we do so far? Linear systems, very basic result. 2 inputs, all I need to do is to add the 2 solutions. That allows me to use the simple property of a delta function to break a general input into a succession of delta functions. Or I can break it into sinusoids. Some people call the first one the Green's method, the second one the Fourier method. And we'll see that they are kind of connected. So now with the Fourier method, we found out that actually the Fourier transform of a function shifted is the Fourier transform of the unshifted function times a phase term. And believe it or not, the structure of whatever you're trying to measure is in keeping track of those shifts. Okay, next property, Parseval's theorem. Do you know what this means physically? So, integral of the modulus square in one domain equals the integral of the modulus square in the other domain. What does that mean? There we go. So, in my little lens setup here, it means that if I come with a certain power here, and I put a big detector, I integrate everything, and I measure, or I put it here, and I measure, I should get the same thing. All the power should be conserved, except for some losses maybe here and here that we ignore. Okay? So, that's conservation of energy. Similarity theorem, another simple looking thing, but with very broad implications. So we talked about what happens if I shift the function to different positions. We know how to deal with that problem. Now what happens if I scale the function? All right? I make it broader. What happens? The Fourier transform gets scaled by the other way around. Okay? And I'm sure some of you have seen this, most of you. But can you tell me physically what that means? Or give me an example where this is important. Yeah, so going back to our diffraction means if I have a field coming onto this pinhole here, or a slit, let's say I get a diffraction pattern that looks like that. This little property helps me understand what happens if I close down the slit. So keep in mind, we didn't prove that far field does the Fourier transform for you, but you believe me. So now I close down this slit, and I'm trying to understand the diffraction pattern of that. What this theorem tells me is that if I reduce the thickness of the slit, the size of the slit by a factor of 2, the Fourier pattern actually, hey, I have colors by the way. The Fourier pattern goes the other way by the same factor. Right? That's useful. You don't need to solve the different problem. All you need to is to solve it for a generic diffraction slit, and then you just scale the result. But now there is also a fundamental implication of this, and that means what happens as I keep closing the slit? Now what? Well, if I make it smaller and smaller, this guy is going to get fatter and fatter, right? Like that, and like that, and so on and so on. But the fundamental problem is that no matter how broad it's going to get, the amount of angles, these spatial frequencies psi, are proportional to these angles. And the best I can do is to measure these angles of 180 degrees from here all the way to here, okay? If I collect everything. But that's basically 2 pi. It's a finite number. It's not infinite. If I want to be able to measure slits that are very, very tiny, I need to be able to do much better than this, to measure somehow angles that are much higher than 2 pi. So right there you see the implications of the nano in the title of our summer school. But actually getting nanoscale information with light is not trivial, just because of this Fourier relationship. That the fact that I can collect only in 2 pi forward means that I can only safely measure slits that are of the order, at best, of lambda over 2, the wavelength, half the wavelength. We're going to do this quantitatively, this calculation in the microscopy. We're going to derive it properly. But I want you to get an intuition for the whole problem from this scaling problem. As I close down the aperture, these angles get broader and broader. Unfortunately, these angles are finite. That's the best I can measure. Which means that if you close down the aperture smaller and smaller, there's lower and lower light that gets on the other side, basically. Okay? So that's what limits us to lambda over 2 measurements in microscopy, in any kind of measurement. And you're going to hear some tricks about going around this during this summer school, how to beat this. Okay, so do you have an understanding for this? What is this in the temporal domain? What would that mean? Can you give me an example in the time domain of this similarity theorem? Come on. You're used to it.
Decreasing the pulse of Decreasing the pulse speed of motion.
Requires what? What happens if I decrease the pulse length by a certain factor? The bandwidth has to be broader. That's right. So that's why the shortest pulses we know how to generate now are from a medium that has a very broad band gain. Okay? That's titanium sapphire lasers. The only reason they generate such short pulses is because they are able to oscillate. They provide gain over very broad frequencies. How about the impossibility of things that we just mentioned here? What would be the fundamental limit in trying to shrink the pulse, making it shorter and shorter?
The on and off switch actually, because it takes some time to basically and that will basically limit.
Okay. And what would that approach, if everything goes well for your experiment? Where would you kind of stop with your pulse? It also turns out it's also related to the frequency. So when the time duration is about 1 over omega, the central frequency of your light, in other words, your pulse is only 1 oscillation short. That's where you kind of hit the wall. People are working on that and try to beat that too. But keep in mind, light comes with this measurement stick, comes with its own scale, basically. This is what I'm trying to tell you. In the spatial domain, think of the wavelength. In time domain, think of the period. Okay? So trying to image beyond lambda over 2 requires special tricks. Trying to compress a pulse beyond 1 period requires certain tricks. Okay? So this simple similarity theorem teaches us a lot of physics. Okay? It's not just a signal processing thing. Okay, so here's summarizing what we just said. I'm trying to make this fat in one domain, it gets skinny in the other domain. And the impossibility of getting an infinitely short pulse is also because it will require an infinite spectrum, which we don't know how to make What's the reverse of this? It's always that there is a reverse discussion that you can have. What happens if I make it skinny here and broad here? What does that mean physically? A continuous wave, okay. This is a continuous wave in time domain. Not only a continuous wave, but an infinite one. Okay, we get into linguistics, but basically what it says is that if I ever want to measure, to do spectroscopy with infinite resolution, okay, that would be nice. That means I'll be able to solve very close states, atomic states, do very good things. Well, the higher the resolution in the frequency domain, the longer I need to measure. That's what this means. An infinite resolution in the spectrum means my measurement is infinitely long, which is kind of impractical. Right? All right. So before we go to the last two properties of the Fourier transforms, we introduce now the convolution, which we already saw before. We didn't have to call it convolution back there, but here it is. This kind of integral of a function with another function that is, you see x prime and the second function has minus x prime in it. It means that this is function 1, this is function 2, then you flip it. Okay, that's the minus sign. And then this is shifting. Okay? I multiply them. That means I multiply, I'm looking at the area of overlap. So this is one function, this is the second function. This is the overlap. This integral means the area of overlap. And this little area gives me 1 point in my convolution calculation. I shift it again to a different position. I calculate again the overlap. I get this, and I will get a different point. Okay? I do this many, many times, which you can kind of tell is annoying. And I get this is the result of G convolved with H. And this is my notation for convolution. We keep cross for cross correlations and V circle for convolution because convolution has a V in it. That's easy to remember. Okay, so you see the meaning of this? Convolution means I flip one of the functions, I translate it, and at each point of translation, each coordinate, I multiply and integrate, which means I calculate the area of overlap. That's just the definition. Correlation between G and H means the same thing except for the flip. So you see one has, convolution has a minus here. This one has the same sign. Okay? These are just definitions, but the interesting part is another definition. If I correlate a function with itself, that's called autocorrelation. Right? That's terminology. Here's a thing you can practice for yourself in case you haven't done this already. If you correlate a rectangular function with itself, you get a triangular looking function. Do you know why? Because I have zero overlap here, and then now the rectangulars start to match, and the area goes up actually linearly with the displacement. So that means I'm on this positive slope. Once they're perfectly overlapped, I get a maximum, and then it comes down. So that's easy to remember, that's a triangle. But in general, if I have kind of bell-shaped functions, not necessarily Gaussian, but let's say there are two Gaussians, and I convolve them. If each of them has a width A, let's say, what will be the width of the convolution? It's going to be bigger or smaller? Bigger. Always bigger. We're going to see how important that is. So if I take two Gaussians, or any function that has a nice behavior, it drops off, and I convolve them, I get something that's fatter. And that's a problem. We'll see it's a problem with our attempt to achieve nanoscale resolution. So here's the convolution theorem. We define what the convolution is. The beautiful result of using Fourier transforms is that if you take the Fourier transform of this convolution, which I just tried to explain that is an annoying process. You shift, you do this integral, and you get 1 point. That's really, I don't like that. So for each point on the graph, you need to do an integral. That's terrible. But if you take the Fourier transform of that convolution, turns out is the product of the Fourier transform. Now you're talking, because products we know how to do very fast. I mean, we know how to do some integrals too, but think about it. Instead of calculating this with the definition, taking the integral of this, I can take the Fourier transform of which, multiply, and if I want to get back to spatial domain, all I need to do is to take the Fourier transform back of that. Are you with me? Let me say this some other way. I'm trying to do f convolved with g. So one way is to do integral blah 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 blah. I don't like it. Another way is to do Fourier transform f tilde of psi, Fourier transform of g, g tilde of psi, and multiply. Okay? And then take the Fourier transform inverse of that. That gives you f convolved with g. That's something. Why? Because now our computers are very efficient in doing Fourier transforms. So if you give me a random input that I know is going to come to my system, and I know the impulse response of the system, that output is going to be a convolution. Okay? So I have two options. I go do this integral, or I take the Fourier transform of the two, multiply Fourier transform back, and I can bet your coffee is going to be much faster this way. Okay? So let's talk about the correlation theorem, and then we'll see what it means physically. Correlation theorem means that if I take the Fourier transform of this correlation integral, it's, again, is the same except that h is conjugated. So the sign in that flip or not flip gives you conjugate or not conjugate in the Fourier transform. Okay, you can, okay. Let me, probably we have 2 minutes, so let's finish this. So that means if I take the Fourier transform of autocorrelation, G correlated with itself.
Can you define how you're using the term conjugate? Can you define how you're using the term conjugate?
How I use the term conjugate? In a regular sense. If I have f equals like, I don't know, a plus ib, f conjugate will be a minus ib. Okay? Or if I have modulus of f times e to the I phi, this will be modulus of f e to the minus I phi. Okay? Yeah, I only made up the symbol for convolution. The rest is standard. Okay? All right, so Fourier transform of an autocorrelation is the Fourier transform of G times the Fourier transform of G conjugate. And that is called, what's the function times its conjugate? Power spectrum. Thank you. That's another very important result. Fourier transform of an autocorrelation is the power spectrum. We'll get back to that at some point later. So let's go back to our problem. Yeah, let's skip this. When are we going back to the Green's function? I think something happened to one of my slides. So the reason we did this, the convolution property, is not just for the sake of math, but to go back to our Green's theorem. If you remember, the problem was like this. This is a linear system, LS, If I have a okay. So let's review the Green's result that we had. This is my linear system. And this is a delta function input. Okay? Delta of t, let's say time domain. What I get output as output is h of t. Okay? And from here, and this is called the Green's function or the impulse response, right? Depending on whether you are an engineer or a physicist. If I input now whatever input I like let's say f of t, or I think we use e of t, we found that actually the output, which will be, what should we call it, g of t, is this integral. The input, e of t, t prime, h of t minus t prime, dt prime. The convolution between my input and the impulse response. What we just found with the Fourier result is that if I take the Fourier transform of the whole thing, I will get this. Let's say g tilde, and I can say omega, the frequency conjugate to time, is actually the Fourier transform of my input, e of omega, times Fourier transform of my impulse response, h tilde of omega. This equation and this equation in time domain are perfectly equivalent. Why? Because the function and its Fourier transform contain the same information. There is nothing lost. But look at how much nicer this is. So all I need to know is the impulse response. I take its Fourier transform and we call that transfer function. These are just names, so they don't matter, but in case you see it. So the transfer function is the Fourier transform of this impulse response. So that means any impulse you give me, I put it in the frequency domain, looks like this. The output will be just the product between these two. Isn't that nice? It is nice. Let me help you. Yes. Okay, I think you need a break, and then we'll come back. Okay. So, any questions?
I was just curious, but I can.
Is it secret?
No, I lost that one. I wanted to apologize for my conjugation question. I knew that when I've been conjugating nanoparticles to antibodies.
Sure, yeah. That's no problem. I know you know what to conjugate. So let me review this, which is a very strong result. May look very simple and innocent, but actually replacing this integral with this product in the frequency domain is a big deal. That's why try to force yourselves to think of any linear problem in the frequency domain. Nature played a trick on us and equipped us with detectors in space and time, right? Our ear, our eyes, everything is space-time. But all the linear problems are solved in the frequency domain much easier. Okay? So it requires a little bit of training to push yourself to think in the frequency domain, but especially spatial frequency domain. For some reason, we have a kind of a much better intuition about the time domain frequencies. Maybe, I don't know, we hear the birds more often or something. We know what 60 hertz means, or 50 hertz if you are in other parts of the world. But it's harder to understand inverse microns and spatial frequencies. But we are going to talk about that in microscopy. So anyway, linear systems much better solved in the frequency domain because of this. Frequency domain output is the product between the frequency domain input and the transfer function, which is the frequency domain impulse response. So you see, whenever you have a product in the frequency domain, you can think of it as this input being filtered by the transfer function. Okay? So products are much nicer than convolution integral. One last property and then we're ready to do some optics. What happens if I take the Fourier transform of a derivative of a function? Well, you can show that actually the Fourier transform of a derivative is I omega times the Fourier transform of a function. Okay, let me say that one more time. If the Fourier transform of f is capital F, the Fourier transform of df dt is I times omega times f. So again, I don't know about you, but to me, multiplying with omega is much easier than taking a derivative, right? So, and by the way, the proof is really easy because f of omega doesn't have t. When I express f of t as the Fourier transform of f of omega, dt goes in here. The derivative of this e to I omega t gives you I omega. What's the meaning of I in the I omega? What's the meaning of multiplying something by I? May look weird if you're not used to it. Yeah.
All the real parts become unreal, all the unreal parts become real.
Okay, that works. Or I can think of it this. I think of it this way. It's e to the I pi over 2. So it's a pi over 2 shift. Okay, that's very important. That pi over 2 makes all the difference in linear systems. Makes the difference from dissipating your signal to conserving your signal, for instance. All right, so try to have a think about this. This is a big result also. That means we can go ahead. First of all, we can generalize this to second order derivatives, which means just I omega times f. So that's minus omega squared. And of course I can do it to nth order derivative, just as easy. As long as I know what I to power n is, that should be no problem. So that means going, man, what happened to my slides? So this whole build-up was to finally have a glorious finish, going back to our equation of motion, mass on a spring, remember that? Okay, we're not going to finish the slides today, just to let you know. You're going to read it by yourselves at home. Plus gamma x dot plus m omega naught squared x equals minus E times E. So this is the electric force. How do I solve this? Using the things that we just learned. So x2 dots means second derivative, x dot is first derivative. How about if I take the Fourier transform of the whole thing? Okay, somebody read it to me. So all this is x of t, x of t. Okay, somebody read it to me. So Fourier transform of this thing is what? M omega times I omega x of omega. I can put tilde to be more correct, basically, plus gamma x dot is I omega x tilde of omega, that's Fourier transform of x, plus m omega naught squared x tilde of omega. So there is nothing going on here, it's just the Fourier transform of x. The rest is a constant, right? These are constant. Equals minus E is a constant, E of omega. So basically, the Fourier transform of my input. So remember, what I want is x of omega. That's what I want to find out. So just learning a couple of properties of Fourier transform, basically a high school student can do it. In the back, right there. Did I tell you we have a recent graduate from the University High School on campus here? There we go. So can you tell me what the solution is? How about to get rid of these m's? There must have been an m here, but so we put this here. So it will be minus e of omega over. I start with this because this is negative, and I like to start with positive. Omega squared naught squared minus this omega squared plus I gamma omega. End of story. So this is the fastest way I know how to solve that equation of motion in the frequency domain. Okay? So I hope you appreciate this. All we did was to do it in the frequency domain. We just established that linear systems, linear differential equations should be solved in the frequency domain. That's the way to do it. From here you can connect actually to the optical response of the medium. So you can get the refractive index as a function of omega. We'll do that, I think, in the next slides. But basically, look how quick this was. What happens if I want to put this now back in time domain? This might be, you might not have a physical intuition for what x of omega means. Inverse Fourier transform. Great. So let me tell you what it means, x of omega. It means that if I'm having a force, or I have a perfectly monochromatic light coming into the system at frequency omega, the displacement in the medium will be exactly x of omega. I change my frequency to a different omega, omega 1, omega 2, then I will get another displacement that will be x of omega 2. If I put them all at once, I have a distribution, e of omega now. The response will be this whole function. Okay? And this complex. Meaning that I have both contributions that are in phase. You see where the I is coming from the dissipation part. So that means I can have displacements that are in phase with my input, and some that are, this I told us that means pi over 2 out of phase with the input. So you can get the physical kind of intuition for what happens when you have dissipation. Is trying to swing a swing, but somehow the displacement is pi over 2 out of phase with your force. You don't get much done. That's what that means. You waste a lot of energy. That's the reason of this dissipation having the I in here, the pi over 2 out of phase response.
I think we just measure the axial distance between the particle and the nucleus. Is that right? This formula measures the axial distance between the particle and the nucleus?
No, it's actually the displacement of the electron with respect to its equilibrium position. Okay? Okay, so we just solved the problem in 2 lines in the frequency domain. If I want to get it in time domain, x of t is basically Fourier transform back of this, e to the I omega t. I forgot whether it's plus or minus, d omega. That's it. Very easy. Any questions before we move on to try to apply some of these things to electromagnetics? So what did we learn? Linear systems allows me to break an input into small pieces, solve each piece, add the results. 2 ways of doing this. One, I break my input into succession of delta functions. I can solve for each delta function, add up the results. That's what is called the Green's method. The result comes out to be a convolution between the input and the impulse response. The Fourier transform means that I can take a signal and decompose it into a summation of cosines, sines and cosines, with varying frequencies, amplitudes, and phases. which means that I can take now the problem, solve it for each frequency, and add up the results. Again, the superposition principle due to the linearity of the problem. Now we brought the two together. The Green's equation and the Fourier transform allows us to express this convolution in terms of a product, which is much easier to do. The system basically acts as a filter in the frequency domain. That H tilde is the transfer function that somehow is modifying the frequency content of your input. Okay? Finally, we found the property of the Fourier transform that allows us to solve differential equations, linear differential equations, very easily, based on the fact that differential operator, Fourier transform of that, is the Fourier transform of the function times I omega. The same thing holds in the spatial domain, meaning if I apply this operator to a certain function, it will give me what? I'm sorry, f of r. This arrow means Fourier transform. What would that give me? I, k, vector. Fourier transform of f of r. K. Now, I can apply this del operator with a cross product, which is called what? What is this called? Huh? F is scalar. Huh?
Gradient.
Gradient, thank you. Gives you this. F is scalar, let's say for now. Now I apply this to F. Now I make it vector. Same thing. Now what happens if I apply another one, a del operator on this scalar one? There we go, that's Laplacian, something to do with the Laplacian. I will get this twice. So with this, basically, we're ready to go to Maxwell's equations. Okay? Yeah. What's the frequency meaning of 2 dimensions, 3 dimensions? See, last year I started with that. I thought this year I should start with 1D and then let you extrapolate to 2D and 3D. Okay, let's talk about that. First of all, let's start with the mathematics. Let's start with 2D. So R is equals, it's a vector like that. Meaning, this is very suitable, very important for imaging systems, right? In an imaging system, I have something like this, X and Y. I have a distribution of stuff here, like my cell or something, that I want to image. In other words, the microscope is my linear system. My input is this cell or whatever the specimen. And I'm trying to understand what I'm going to get on the other side of the microscope, the output. And since we established that frequency domain relationship, it would be nice to understand for me what it means to have a Fourier transform in 2D. So, in the same way, we use the Fourier relationship in time or in 1D. I can write the same thing here as f of k, which is kx and ky, e to the I, kx times x. So now this is a scalar product, see? So I have kx times x plus ky times y, dkx, dkx, dky. What does it mean? It means that in the frequency domain, kx, ky, say something like this, I can have I'm trying to kind of draw in 3D a little bit. It doesn't quite work, but You know when you are on the airplane and you look down on the surface of the ocean and you see these ripples? They're not perfect sinusoids, right? But you can think of them as a superposition of sinusoids going now not only in 1D, but they can go in 2D. Okay? So that's basically what I'm trying to draw here. You have a surface, right? Could be your sample. A surface that is kind of rippled in an irregular way. The Fourier transform in 2D says that I can decompose that into a sinusoid of this frequency along this direction, and then another frequency, and another frequency, and another frequency with the proper amplitude and shifts, except that now I have the other direction also. Right? I can do the same thing along the Y. So the concept is basically the same. Now in 3D, it's the same idea. I have a 3D object, okay? You can think of an MRI tomography. You decompose that now in sinusoids, different amplitudes, different frequencies, different phases, except that now I have 3 dimensions, so I can overlap these sinusoids along 3 different directions. So of course the frequency is also a vector to take care of that. So I can have frequency along X, conjugate with X, frequency along Y, and frequency along Z. Now, we're going to see how, from Maxwell's equations, we can define a vector that is perpendicular to the wavefront of the light. So imagine this is a distributional field that is perfectly constant, perfectly flat. I can define a normal at that surface, and I can call that a wave vector. Now, imagine for a second I have 2 of these waves, like this, propagating like that. What's going to happen, let's say, vector 1 and vector 2, what's going to happen here when they meet? Similar to the Young interferometer, I have 2 beams coming from a little bit off, right, at an angle. What's going to happen? I have an interference, right? Fringes. There we go. Now, it turns out that fringe is exactly sinusoid. From what we just proved, there is a cosine in there and so on. So what I'm trying to tell you is that for each sinusoidal distribution of field, you can make that sinusoid out of 2 wave vectors. So basically, each wave vector has a component along the fringe and one perpendicular to it. The one perpendicular to the ones this way don't give you the fringe. What gives you is the counter-propagating ones. I drew them wrong already. They have to be counter-propagating like this. So you see the sinusoid is given by the components of the k vectors that are coming toward one another. That means each cosine is made of a e to the I k something and an e to the minus k something. Let me write this again. We're talking about this plane wave coming like this, and then this plane wave coming this way. So I'm zooming on the k vectors. I have this, and then I have this. The fringes are going to happen on a line that connects the 2. The difference vector, k2 minus k1. Right? The vector difference between this k1 and k2 is this vector that connects the tip of one to the other one. And the component of the k2 that's parallel to k1, so in other words, this component, doesn't give you any fringe. What gives you the fringe is the counter-propagating component. In other words, to get a perfect sinusoid, I need to get this k vector and this k vector. So what I'm trying to explain to you is that these wave vectors are actually the variables that will show up in the Fourier transforms. Right? So what we learn in the Fourier transform is that we can decompose any distribution of anything, including distributions of field, by summation of these sinusoids. Okay? Two counterpropagating waves, they give you a distribution, a sinusoidal distribution. They are made of a k positive and another k negative. In other words, something like e to the I k1x plus e to the minus k1x, assuming this is x. So with this physical meaning, it means that I can solve now the spatial distribution. I already have a good feeling about the time domain part. I can go now full force to the Maxwell's equations, and with this understanding of the importance of the wave vector, I can apply my Fourier relationship and properties. Yep.
Sorry, I've never heard this explained this way. Are you saying that basically only one component of each of the k vectors is one that contributes to the differential? Or is it not going to?
Each component of the wave vector?
You drew the k vectors like this.
Yeah.
And I'm just...
You're trying to understand where it's coming from? Well, let's write the fields together. So I have, let's say, field 1 will be, let's forget about the amplitudes, okay? Amplitude 1, e to the I, k1 times r. And I have u2, e to the I, k2 times r. These are plane waves, and I draw them like this. This is k1, this is k2. One is going this way, one is going this way. Let's see what happens when we overlap them. Okay? So I have u1 plus u2, right? And now what happens if I take the modulus square? Let's say I'm looking at the intensities. I get modulus of this, which is 1, plus modulus of this, 1, plus 2 times this times this, plus this times this conjugate, plus this times this conjugate. Okay? So let's write it like this. E to the I k1 minus k2 r plus e to the minus k1 minus k2 r.
Should that be minus I times?
Yes, I. Thank you. Yes. So let's see, what does it mean? It means that all that matters is this difference, which is, that's the reason I wrote k directly, because I knew the answer. So it means that it's a, are you guys with me? Scalar product between this wave vector difference and r. Right?
Where's the minus come from?
The minus, which minus?
Minus k2.
It's from here. When you write these modulus, it's this conjugate times this, plus this times that conjugate. Right? So it means that I only have, okay, if I expand this, I get something like 2 plus 2 times cosine of q times r. So now what is 2 plus 2 times cosine of qx times x plus qy times y. Okay? So that means that I'm going to have oscillations. The cosine is going to be showing only where q is parallel to r. Right? Which means along this direction. That's what the scalar product gives you, right? It gives you the parallel. It's only showing when the two vectors are parallel. So it means that I'm going to have an intensity that's modulated by this cosine exactly along the direction of the difference in the two k vectors. Okay? So now what that means is that I can decompose a complicated distribution of fields. Imagine now I have a bunch of other plane waves coming in, right? Over different directions. We're going to talk about what the plane wave decomposition means. But basically, any beam that comes out of your laser, intuitively speaking, you can think of it, if this is your beam, you can define locally a plane wave, a tangent to that wavefront. And you can think of it this way. So like usual, when you understand the problem for two things, then you can extrapolate to n things, right? Like we did with the diffraction, right? So if we understand how the problem of two wave vectors works, which is this, it means that I can extrapolate to a continuous distribution of k's, but now Fourier transforms are very useful. Because basically what we establish here is that I have a cosine decomposition given by these two counter-propagating k vectors. Okay? And going to this is kind of a full circle. Now we are going to use the Fourier transform properties extrapolated to 2D and 3D just by using the differential operator, which now becomes the del operator. But the same properties kind of hold in terms of the frequency domain. Okay? So I've been trying to give you the physical meaning of these k vectors, which is very, very important. And not surprisingly now, that's how we like to solve the problems. If you want to send your laser beam to an anisotropic crystal, good luck solving that in the spatial domain. Okay? If you solve a birefringent wave equation, you're going to have a very hard time. The way to solve it, you go into the K space, and you're looking at how the wavefronts are kind of propagating. And then the problem breaks down nicely. So you end up with some ellipsoids where the K vectors can propagate. So again, this is the spatial domain equivalent of the Fourier transform, where again the Fourier properties are very important. In practice, we never have monochromatic light, a single omega, or a single k. Okay, monochromatic light means single omega. Single k means what? Plane wave. Okay? These are the analog of one another. We never have that. Why? For the reason, for one thing, for the property of the Fourier transform, that if I have this plane wave with the delta function in k, it requires that the plane wave is infinitely broad. Okay? So that's not possible. If I have a purely monochromatic laser, that means it takes forever. Okay? So who's there to turn it on? So we always have a broad distribution in omega and in k. But what we just established is that the way to solve these problems, like a beam, which is made of many k vectors, and the broad bandwidth distribution, these are solved best in the frequency domain, solving one color at a time and one k at a time, basically. That's all we're trying to do. What do you think? How many of you are, I think I asked you before, how many of you ever solved the Maxwell's equation? Solved, not most textbooks say, oh, show that this is a solution. Part of your qualifier exam? To solve it. How did you solve it during the qualifier exam? See, the point of the qualifier is not to pass it and forget everything. Anyway, my point is that most books, or at least those that I read, usually say, okay, that's pretty vague for an engineer right there. So most books say, show that the spherical wave is a solution of the wave equation. So then what do? You plug it in and you show that the derivatives add up, and that is a solution. What I'm going to show you today is how to do it using what we learned today. I mean, it's not a big deal. Everybody knows that the spherical wave is a solution in 3D. If you have a point source, the light coming out, it will look like a spherical wave in a certain way. And if I have a, let's say, a very flat source, the solution of that will be a plane wave. If I have an infinitely broad flat source that will emit along one direction, that will be a plane wave. We're going to take a look at how to solve those. But first, I want to review Maxwell's equations. You're going to have lectures on plasmonics. And this is kind of the easy version of what you're going to see in plasmonics. But kind of just to make sure we know the definitions and we're on the same page. This first equation here is called Faraday's induction law. Tells you that if you have a magnetic field that varies in time, that means this one, that generates an electric field that is rotating. Okay? Do you know the definition of the curl operator? Mathematically, with that determinant, remember that? Probably part of the qualifier. Okay? So that's that. Having a varying magnetic field generates some kind of electric field. This equation tells you exactly, if you know the components of B, you can take the components of E and just find them. Right here, you note E and B are coupled. Okay, that's the fundamental kind of principle of electromagnetics. Now, Ampere's law tells you that if you have an electric field that oscillates, or that varies in time, okay, like a wire, and you send the current through it, you are going to generate a magnetic field right here. That will look in a certain way. The components of this field you can calculate using that equation, but just plugging in. If I know D, let's forget about these currents for now. Let's forget about these. If I have just D, and it's varying in a certain way, and I know the D components, I just plug it in, do an honest job, and get H out. Okay, that's what these equations are telling you. Now, this is, I think, what is called Maxwell's corrections. Is that you can have a source like an antenna that has a certain current through it, and that's why we call it JS. This is a density of current. Okay, it's a surface thing. And I can have a conduction current of the form sigma E. In other words, something that will happen in high conductivity materials like metals that you told me earlier. Okay? What that means, this current means, first of all, I can have a certain, just a current that I plug in there and it's flowing through. Not so much in optics. We're moving towards that. The scales are too small, but very common in antennas. Right? That's how your TV used to work. Some of you are too young to have seen that. I've seen it. I was on top of the house doing that. So you run a current through the antenna and you generate waves, and somebody's catching them the other way around at a certain distance. Get that field, generate some currents in your antenna, and then you detect that. So that's the source current. The more interesting part in optics is the conduction current. That when I apply my optical field, the electric component of that optical field is driving the charge, as we just established earlier, and generates local currents of some sort. And in the process, because I have conduction, I'm going to have loss. Okay? So that's the meaning of these J's. But anyway, the question here is, my input is the J's. You give me all the coordinates of J's. You give me all the coordinates of these. That's my input. I just plug it in, do an honest calculation, I get H out. Okay? Okay, these are all definitions. I'll let you go through all these. I'm trying to kind of summarize the meaning of them, okay? So let's see what we have so far. We have E's, we have H's, but unfortunately, on the right-hand side, we have B's and we have D's. That complicates things a little bit. How is D different from E? Anybody? Permittive. So what does that mean in English? Like, okay, epsilon is English for you. I know you know what it means, but what it means is that it has the property of the material in there. Okay? So it's not only the field, but it matters whether the electric field is in a metal or in a glass or in water or in air. That's why we need to take that into account. So this has an epsilon and this has a mu, another English letter. So we need to put all these into account. Therefore, we have two more equations here about D's and B's, and then finally the material properties that are connected. See? So epsilon comes in here, mu comes connecting H and B, and this is the equation that I just showed you for the conduction currents. Okay. So I have divergence of D equals rho. This is Gauss's equation. Okay, in an integral form, it means that if I have a distribution of charge, so rho is the charge density, right? How much charge I have per unit volume. Basically, what that equation says in an integral form is that if I integrate around this charge, I get the total flux coming out. Okay? Now, for B's, I get 0, meaning what?
Flux that goes out comes back. So.
Yes. In other words, meaning that we couldn't find the magnetic charge yet, the equivalent of the electric charge, which means exactly what you said, that there is never a magnetic field going this way, like out from an electron. It's always coming back. Good. So this establishes that there is no magnetic monopole. Okay? Good. Now we have these equations, right? So we have 1, 2, 3, 4. These are the main equations, and then the material constitutive relationships. Before we go to the boundary conditions, let's stop here for a while. We have at the material part. So we have D equals epsilon times E, and we have B equals mu times H. What does it mean that these two bars, that I put these two bars here? What do you think? It's just a notation. It means that this is a tensor. In other words, in the most general case, I have dx, dy, dz equals a matrix exx, epsilon xx, epsilon xy, epsilon xz, blah blah blah, epsilon zz times ex, ey, ez. What does it mean?
Different directions. It's different. The properties are different.
Along different directions. Very good. So that means the response of the medium, shown in that matrix, is different along different directions. In other words, if I apply my electric field to the crystal, this is crucial for crystals where some of them are highly anisotropic. If I apply my electric field along x direction or along y or along z, I get different things. Another way of saying this is that if the material is isotropic, means that D is always parallel to E. My electric field is along this way. D is also parallel to this. In an anisotropic, it doesn't mean that. In fact, I can always have D and E not parallel at an angle with respect to one another. Very important. So one thing is anisotropy. And that's what we do in crystals. That's the birefringence I mentioned earlier. You need to go to the spatial frequencies, the k-vector domain, to solve this problem. Otherwise, you're in big complications. What else can happen? So anisotropy means epsilon and mu are tensors, are matrices. What other complication can we have?
Can we have anisotropy in homogeneous environment?
Huh?
Can we have anisotropy in homogeneous environment?
Anisotropy and inhomogeneous?
Inhomogeneous.
Inhomogeneous. Okay. Inhomogeneous, yes, the answer is yes. That's a mess, but yes. So the other thing is epsilon as a function of r. Epsilon is a scalar, not a matrix anymore, it's a number. But the trouble is now it varies from point to point. We call that inhomogeneous. And you see I'm ignoring mu because usually we deal with non-magnetic materials most of the time. And inhomogeneous, if you're brave enough, you can have inhomogeneous and anisotropic. How would you do that? You take a piece of crystal, anisotropic material, you grind it up, make a powder, and try to understand how the light scatters in that. Some people have done that. Like second harmonic generators in powders, it's a mess, but you get something out. So that would be inhomogeneous and anisotropic. That works. So basically inhomogeneous, all the problems related to scattering. Solving an inverse problem means from the light scattered on these inhomogeneous media, being your live cell or your photonic crystal or whatever, I measure the scattered light, somehow put all the data together to extract epsilon from that. That means solving the inverse problem. Remember, what we talked so far was the direct problem. You give me the input, you give me the system, you give me H. The equivalent of H is my epsilon now, right? That defines my system. Direct problem, you give me the input, you give me H, I calculate the output. Unfortunately, for us experimentalists, the problem is backwards. I can prepare my input the way I want, and that's where good experimentalists and bad experimentalists are different. I prepare my input, I measure the output the best I can, but the goal is to get back to the system properties, which is unknown. Inverse problem, okay? Okay, so inhomogeneous, that's a scattering problem. What else can we have? How about epsilon of omega? What's that complication about? Dispersion, thank you. Some people call this inhomogeneous spatially dispersive media, which is okay. Okay? So you see it's the same thing. This is the distribution in spatial domain. This is distribution in the frequency domain. They mean the same thing. Dispersion. Now, where is that useful in imaging? First of all, let me ask you in time domain. Where is it? Why is dispersion important in time domain? What can that do? Pulse spreading. So you see, we always, even if I start with a very tiny pulse, what I get on the other end is a spread out pulse. And believe it or not, this spread out comes from the fact that H is a function of omega. Is due to dispersion. So can you think of an example where that's crucial? Fiber optics, yes. Okay? You want to compensate the dispersion as much as possible such that your pulse stays the way you put it in. If this spreads over to the next pulse and the next pulse and so on, your internet is going to get messed up, right? So dispersion is very important in time domain in communication. There is no question about it. But also, coupled somehow, sneaks into the spatial domain when you do imaging. Okay, so let's say time domain. Why is that? Well, basically, epsilon is something like the refractive index squared. So the fact that the refractive index depends on the wavelength or on the frequency means that I have an imaging system like my microscope or your digital camera, that video camera, pretty good, is actually imaging with white light. So unless you pay attention to the dispersion properties of all the lenses in your system, you're going to have the red light focused at one point and then yellow light at a different point and so on, all the way to the blue. Basically, the image will be smeared. It's going to be very unpleasant. Okay, so spatially that is called chromatic aberration or color aberration. I mean, these are just examples. There are many other areas where dispersion is very important. What else can we have? We can have one more thing. So you see, in space and time, there are only two things you can have, right? Function of r, meaning function of k, the same thing. And then, what does it mean in the time domain, the fact that epsilon, Fourier transform of that will be epsilon of t? What does that mean? So it's funny that we have a good feeling for dispersion in the frequency, in the colors now, but we lost our kind of meaning in the time domain. What does that mean? I wouldn't know.
Property changes.
Properties change. So during the pulse interaction with my material, the response, let's say at the beginning of the pulse, when the pulse hit the materials, is not changing. By the time the middle of the pulse is in and the end of the pulse, that response changed. Thank you. Okay, one last thing. What else can we have? We kept talking about linear systems. How about nonlinear system? What does that mean? It means epsilon is a function of E. Like we said in the beginning, I turn up the power of the laser. That means the electric field goes up. Then my epsilon starts to change. Okay? So remember, we had D equals epsilon times E. And by the way, all nonlinear crystals are also anisotropic, but let's not worry about that. Let's not worry about anisotropy for now. So this is the linear case. In nonlinear case, if epsilon is a function of E, I can probably expand it in a Taylor series as a function of E, and I end up with something that will be D is epsilon 0 E plus epsilon 1 E squared plus blah 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 blah. Okay? But I should be more careful with what is here. This should be Ij di ij ej and then epsilon ij k e. I messed up. Let's write it correctly. Ready? D in the most general case is epsilon ij, right? D I is epsilon ij ej. This is the linear part. Plus epsilon ij k ej ek plus epsilon ij k l ej ek el, and so on and so on. So this is the second order nonlinearity that you're going to hear about today, I think. So if these are equal, I will have something like E squared. If you have e to the I omega t, that squared gives you 2 omega. So that's the term that gives you second harmonic generation. And then this is the third order nonlinearity that has 200, how many terms? Who works with nonlinear optics here? Nonlinear optics specialist, I'm not the one. You are? How many terms in the chi-3 nonlinearities? Total. 27. Oh, you're talking about the chi-3, but I'm talking about the combination of the terms. 250, it's 3 to power 6, I think. So that's more than, anyway, more than 200. So all this combination means that I can get third harmonic generation, right? If I put all these without any conjugate, I get e to the I 3 omega t. But if I put conjugate on one of them, the omega cancel out here, so I end up with the same omega. But the refractive index depends on E, and that's called self-phase modulation. So I turn up the power, and the refractive index actually is changing as I turn up my power, as I play with my power. The frequency stays the same. So this is only one term in the whole combination. Cross-phase modulation, I have two beams, different polarizations, I put them together, and so on and so on and so on. So you have many, many terms here. You have another term here when one is like this. What's going to happen? In the second harmonic case, I mean, it's no longer second harmonic if I have one with a conjugate. What do I get? I get omega minus omega, right? I get 0. This becomes DC. It's called, do you know what it's called? Optical rectification. In the 50s, in the 60s, theorists started to predict all these things, and one by one, experimentally started to kind of demonstrate them in the lab. So this was kind of surprising, that you get a DC electric field in a material from optics, basically, from optical fields. Anyway, so the fourth thing I wanted to discuss with you is the fact that epsilon can depend on the actual electric field. And we need to be careful with all our linear system discussion because it's a new story. We always have to linearize the problem somehow, otherwise it becomes untractable, otherwise we need to run on computers. But basically, once you have powers other than 1 in the E's, we need to be careful. So we have epsilon as a matrix, right? An isotropy, epsilon depends on the on the direction of the electric field. We have epsilon as a function that's a scalar, but is a function of omega. That's dispersion. It's a function of space. That's scattering. For imaging, that's what we are after. As a function of omega, of course, all the field of spectroscopy is dealing with that. And then we have epsilon as a function of V, which is the nonlinear response. Okay. How about we go for 15 more minutes, then we go for lunch. Are you okay without another break? It's impractical to take a break now. Okay, so I'm going to fly very quickly through this. So the problem is like this. What happens if I have different media now? So I'm trying to understand how the field distribution happens when I start in one medium and I go in another medium. The light bends right there. So that's one picture. That's right there is a geometrical optics picture. So I have a ray, infinitely thin thread of light. Frequency? Spatial frequency? Direction is fine. So k vectors have to change somehow, right? Changes how? Okay, so yes, the waves changes wavelength, not frequency. Okay, so in all media, the frequencies stay the same. Why? Because my field is driving the electronic charge, right? The way we discussed in the beginning. So this frequency is always the same. But the velocity changes depending on the refractive index. So in other words, what's the distance that the light propagates during this one oscillation? Becomes bigger or smaller depending on the refractive index, how fast the light propagates, okay? Try to make sure you understand the difference between frequency and wavelength, okay? Frequency doesn't have material properties in it. Wavelength does. Lambda over n, lambda vacuum over n gives you the lambda in the medium. Okay, that's what you drew there, right? Okay, well, but now let's get even more scientific. What happens if I come with a electric field with the full vector distribution. So I have 3 components of the electric field coming at this interface at the particular direction. So I have a particular K distribution. I have a whole beam, right? It's a mess. How do I deal with that? Well, boundary conditions are the following. Basically, the electric field in the plane of separation and the magnetic field in the plane of separations are continuous, except for some situations that I'm going to tell you. And so E and H in the plane are conserved. But normal components of D and B are conserved. Okay? So E and H in the plane, tangential components are continuous. Normal components of D and B are continuous. That's all you need to know. Everything else follows from here. The Snell's law, the fact that the angle changes somehow with the signs, you know all that. It comes out of here. Even more, how much field do I get for each component of the electric field? Basically, the Fresnel equation that gives you the reflection and transmission coefficients for each polarization. They all come from here. I have them all derived here. Probably I'll fly very quickly. But this is the bottom line. Once you have an interface, you need some kind of boundary conditions. You need to connect the two media somehow. I know how to propagate here. I know how to propagate here. Just use the Maxwell's equations. But now how do I connect them? That's what boundary conditions do, right? Okay. So that's what I was telling you. N is the normal at the interface. N cross means everything that's not parallel to N, right? So N cross means the tangential component of E1 equals the tangential component of E2. That's what this 0 means. The same thing for H, except when that interface happens to have currents through it. That's the situation that I was telling you, it's an exception. For most optical systems in our labs, that's almost always 0. Now, N dot gives you the normal components of D and B. They are conserved, except when you have charges. Free charges at the interface. Okay? Again, most of the time we don't have that in most materials. So that also is 0 most of the time. Okay? So E and H in the plane conserved. D and B normal conserved. That's all you need to know. Okay. So from Maxwell's equations in time and space, which we did before, we're going to look at Maxwell's equations in space and frequency. R and omega. And we're going to use this little thing that we beat to death today. And let's see what happens. Well, very nice things. The derivative up there gives you I omega, right, with a minus, because we had minus d at dt right here. Here I omega, and also d is as a function of r and omega. And all these j's that usually I don't really care about, especially this one. I don't have source currents. But the bottom line is this. That's a perfectly equivalent set of equations with the Maxwell's equations, except that it's as if instead of applying it to a pulse or a temporal distribution of the field that could be very general, irregular, it's as if I'm looking at one color at a time. What happens at omega if I make this particular frequency omega 1? This is what happens. Constitutive relationships are the same thing. Okay? Of course, if this is a function of omega, then you need to be careful. Right? If epsilon is dispersive, if epsilon is a function of time, when you have d of time equals epsilon of time times e of time, when I take the Fourier transform of this guy, what happens? I have d of omega equals epsilon, I should put tilde just, Here I don't have tildes, but you understand d in as a function of omega is a totally different function than d of time. Okay? Epsilon tilde of omega convolved with the field of omega. Okay, but if we assume epsilon and mu for now don't have a frequency dependent, then let's forget about that. Next one, we look at the boundary conditions, and it has the same form. Nothing is changing there. In other words, the boundary condition holds for each and every color, each and every frequency. Okay, that's useful. Now, maybe most of you have heard of the Helmholtz equation, right? How many? Okay. So, Helmholtz equation is actually the wave equation in the R, space and frequency domain. So basically, what we're trying to do is to eliminate H from these two equations and end up with an equation only in E. That's the usual way we solve Maxwell's equations, right? Now, quick question. Why do we care so much about E and not so much about H? You what? Okay, but why do we focus so much on E? I've never used an H one myself. You can.
You can measure E.
Right. Our detectors are responsive to E. Okay? At least most detectors. So that's the reason. You can have a perfectly equivalent equation in H. There's no problem with that. We know they're perfectly equivalent. Anyway, so that's why we do it. So we apply a curl here. You see what I'm trying to do? If I add a curl here, I have this equation that already has the curl in it. So basically I apply this curl here. I use the property of the curl of curl right here. And we're going to get the divergence of V equals 0. So I end up only with the Laplacian. I'm sure you've done that before. So we end up with an equation that's particularly nice and easy. Laplacian of V plus something, beta squared of omega, times E equals 0. So you see there is no time derivative. Why? Because in the frequency domain that gives you omega squared, which is right here. And omega means that that little term, I omega mu sigma, the fact that we have omega to power 1 means that that term originated in the first order derivative. Right? And we can have a long discussion about first order derivative versus second order derivative. You see, this is the dissipation part. Do you know an equation where actually it's very similar to the wave equation, except that the time derivative is a first order, not a second order? For instance, what is this called? Lambda Laplacian of U of R and T plus something 1 over D du at dt. What is this called? Huh? I have a derivative of time here. Diffusion equation, thank you. Was that from the high school guy? Good job. Fresh undergrad, by the way. Okay, that's the diffusion equation. Well, what's the difference between the diffusion equation and the wave equation? Physically, diffusion equation describes this phenomenon. I have a drop of ink, drop it in a glass of water. It's telling me what happens, how that spreads around. Wave equation tells me, okay, I have a point source, I let it spread, and it tells me how it's going to look like far away. Now the difference is, I can get the light back in with some lenses or something, if I'm careful. I can put it back where it came from and so on. But good luck with trying to put the ink back where it came from in a glass of water. Think about that for a second. All the difference is that this is a first order derivative, the other one is not. It's a second order derivative, which means that this has omega and this has not. And also the first order derivative gives you pi over 2 phase shift, and this doesn't. It gives you 2 pi over 2 phase shifts. Basically what I'm trying to say is that this little difference here tells you it's the difference between a reversible phenomenon and an irreversible phenomenon. Okay? I asked a student in my class this semester to give me other examples of irreversible phenomena, so I'm going to ask you the same thing. I got the cool one. Give me an example of another irreversible phenomenon.
Like heat transfer from a high temperature to a low temperature.
Okay. You don't need to say where from where. Yes, that's true. That's too close to the diffusion equation. Something else. Source? What? Source and sink? Okay. I'm not sure what that means exactly, but... Oh, come on, something else, like aging. How about that? Talk about it. Anyway, the response I got in the class was frying an egg, which I thought was pretty cool. That kind of matches the heat transfer right there. Anyway, so I'm trying to give you a physical meaning of what all these little functions here mean. So again, this is dissipation. That means you lost the information if you want. There's no way you can recover that. But this is actually the recovery part. So it's like the elastic part and the dissipation part. Going back to the spring. Okay, so beta, in any case, beta is a material property. Okay, it comes with the crystal, with your material. E is your input. All we want to find out is how does E propagate farther away from that material. Well, if in a Cartesian coordinate system, you can break that vector equation to a set of 3 independent component equations. So you can solve it for each equation over E. And I bragged that I'm going to show you how to solve it, but I think I didn't. So I just ask you to believe me that this is the solution. This is a plane wave solution to the wave equation. How would we solve this? And with this we take a break. So let's solve for the plane wave solution. That means this is the problem. I have, let's say, a source that's infinitely wide at a certain position in X, and I'm trying to find the field far away from that source. How do I solve this? Well, I have my little equation here, Laplacian of V of X of R and omega plus beta squared. I mean, let's say we're in vacuum, so this is beta naught. There is no R or omega in it. U of X of, I should call it maybe X, we're in one dimension, X and omega, equals a delta function in X. And maybe some kind of functional spectrum if I want to be more rigorous. So what it means, a delta function in X means I have something here at X equals 0, nothing else along X, but it's also constant. It's like times 1 for the Y direction times 1 for the Z direction. So that means it's infinitely broad in both Y and Z. It's an impulse along X. How do we solve this? Fourier, thank you. That makes me so happy. So, okay. We take the Fourier transform of the Laplacian. Let me write this down again. Ex plus beta naught squared Ex equals something of omega, let's say a certain spectrum, A of omega delta of X. Boom. Take Fourier transform with respect to space, right? So this is a function of X. Function of X. So that gives me minus what? K squared. Let's call it Kx squared. Okay? So this is the K along the X coordinate. Plus beta naught squared, same thing, oops, and I can factor this since I forgot to write it there. This is the Fourier transform of E of x as a function of kx and omega. That's how we rigorously should write it. A of omega stays A of omega, and the Fourier transform of a delta function, 1. Thank you. There we go. The solution to this impulse response, the solution to this impulse gives me the impulse response, which is Ex of kx and omega is whatever this function, A of omega, over beta naught squared minus kx squared. Believe it or not, that means we solved the wave equation in one dimension. Looks weird, right? You are not used to it in the case. If you are like me, I wasn't too familiar with this form of the wave equation when I was an undergrad. So what do? We go back to x domain, right? So let's say Ex of x and omega is the Fourier transform of this guy. Do you know off the top of your head what that is? Sine and cosine, okay. You know the response, the result, of course. But let me kind of trick you a little bit. Beta naught squared plus I kx everything squared. As a function of kx, if I call this t, or not t is bad, let's call it u. As a function of u, what is this function called? One over 1 plus x squared. What is that function called? Lorentzian. Thank you. What's the Fourier transform of a Lorentzian? What's the line width of a natural? What's the natural line width shape spectrally? Let me help you. It's a Lorentzian. That is because you have an exponential decay time between the two levels. What I'm trying to say is that 1 over 1 plus x squared, the Fourier transform of that is e to the minus x with a modulus. Okay? Going back means the Fourier transform of this should be something like e to the I k, we need to massage this a little bit. See? A of omega 1 plus I kx over beta naught everything squared. So you see it's a Lorentzian that has a width beta naught. You with me? Whatever I put at the bottom here of the variable gives me the width of that function, right? So this comes up due to our similarity theorem. And it's much easier when you know the result, isn't it? Beta naught times x, so kx becomes x, right? And with a minus, maybe. Doesn't matter. And if you're doing everything right, it's also over beta naught. But that matters less. Huh? And A of omega, yeah. Now, what is this? It's a field whose amplitude is constant as a function of x. Right? That's a plane wave right there. The phase of the plane wave as it propagates through x varies with the frequency beta naught. Spatial frequency beta naught. This tells you how many radians per meter you accumulate. So basically the wave equation couples the input field, that was this delta function, with the material properties, which is beta naught, right? So beta naught is now omega over c if we don't have any conductivity, right? That's the wave number associated with vacuum. So this has the wavelength in it, the frequency in it. So basically this is the plane wave solution, right? No? Why do we always write it as a vector Because here there is no vector because it's along x. Well, imagine now I have my propagation rotated with respect to the coordinate system. In that case, I need to have a product like k times r because the phase advance is only on the direction perpendicular, on direction parallel to k, perpendicular to the wavefront, and not in this way. But basically, a plane wave means a one-dimensional propagation. And it's only up to you to pick your coordinate system right, so that you don't need to do the dot product. You can write it like this. Now, finally, before we go to lunch, from what we learned today, what happens now if I have a source that is not a delta function at origin in x, but somehow it looks like that? Not a very practical source that you will see in the lab because it only varies along one dimension and it's infinite in the other two dimensions, but just for the sake of argument. How would we solve that problem? Let's call it S of x. Convolution, who said that? Very good. So basically what we showed is that the plane wave is the impulse response for this one-dimensional propagation. So if the source is a function of S of x, the final result will be my field along x will be the convolution with whatever this one is. I could call it h of x. What's a convolution with a complex exponential like that? In general, the Fourier transform will be a multiplication, but there is something specific about convolution with the complex exponential. I'll let you figure that out. Okay, so we solved the plane wave. So we found the plane wave solution just using our Fourier transform tricks. I know everybody knew the plane waves, but that's the way to connect what we learned today.